did just sort of a recap of our first 5 tests. We have the geometric series test, the nth term test for divergence, the integral test, and the harmonic and p-series. We also have telescoping. So here I've got screenshot in 5 different series. And what I had them do in class is I first said spot the one that looks geometric to you. And remember that geometric looks like a, some number, times a common ratio r to the nth power. The only one that looks remotely like that would be this one over here with the -3 to the n plus 1. It would need some reworking, so we'd have to write it as -3 to the nth times -3 to the first. On the bottom we'd have to have 8 to the nth. Our common ratio then would be -3/8 to the nth, and then we'd have that -3 as our term out front. Remember, when the absolute value of that common ratio, in that case -3/8, and its absolute value would be 3/8. When that's less than 1, we'll converge. Think of exponential decay. When it's greater than 1, the geometric series will diverge. Then I said which one's set up for the nth term test for divergence, where you run a limit or send n to infinity, and you clearly don't get 0. And they chose this one in the bottom right because the limit as n approaches infinity of n squared minus 1 over n squared plus 1, when n is the new x, so like x squared minus 1 over x squared plus x, is 1, which does not equal 0. Therefore, the series diverges by the nth term test for divergence. Remember, when the limit is 0, we're inconclusive with the nth term test for divergence. When the limit's not 0, it means we're going to continually be adding something that's not approaching 0 to the aggregate sum. And so the series will diverge by the nth term test. I then skipped down to this last one with the p-series. From your notes on Friday, those are of the form 1 over n to a power, or 1 over n to the p. I talked about how the harmonic series is 1 over n to the first, and I called it the divergent harmonic. It's sort of like the fence for divergence for your p-series. Any p-value greater than 1, like 1 over n squared, 1 over n cubed, 1 over n to the pi, will converge. It'll go to 0 faster than 1 over n to the first, and fast enough to converge. Any p-value less than or equal to 1, and the p-series will diverge. So this one on the bottom left is a p-series with p equal to pi, which is greater than 1. Therefore, this series converges by the p-series test. The one that's set up for telescoping would be this one in the top left. It'll also be easy to do that one after tomorrow another way. So the one that sort of lends itself to the integral test is this one in the top right. Without the root ln n, I have the divergent harmonic. But adding some more weight to the bottom is going to cause that to go to 0 faster. Will it go to 0 fast enough to converge? I don't know until I run another test. And that's one, usually ln is sort of a trigger for the integral test. That's one where I'd run the integral test on it. So here's what you need to know. The geometric series, what makes it converge or diverge? The absolute value of the common ratio or absolute value of r. When it's less than 1, we have convergence. Greater than 1, we have divergence. To what does it converge? It converges to a over 1 minus r. Can you rewrite some complicated ones like that one on the past screen to get them in the right form? A times r to the n. The nth term test for divergence. It's a one-way test. Make sure you know that you can never say something converges by the nth term test. Know that you take that limit as you send n to infinity, and if you do not get 0, then you conclude divergence by this test. If you do get 0, this test is inconclusive and you need another test. Telescoping is not on the AP test, but you should know how to expand it. You should know it usually lends itself to some partial fraction decomposition, or it's already expanded. And when you start plugging those n values in, things start to telescope or collapse, and it converges to what it collapses to. Our p-series, what makes it converge? It's 1 over n to the p. Convergence would be when p is greater than 1. 1 over n cubed, 1 over n to the fourth, 1 over n to the fifth, those go to 0 very quickly. 1 over n to the first is the fence for divergence. When n is less than or equal to 1, the p-series will diverge. The integral test is our trickiest one. When can we use it? We can use it when we have f of x replacing the rule of sequence, and f of x is continuous, decreasing, and positive. Those can just be verified at a glance. You don't have to verify them with calculus. It's usually quite clear. What integral do I use? I replace the n in the rule of sequence with an x, so I have an f of x dx. Remember, we use that formal limit notation when we go to infinity. If the integral converges, so does the series, but not to the same value. And then the last part of that we haven't done yet. So now, to be continued, we need to discuss the limit comparison test and the direct comparison test. Those we'll do together. Then we'll move on to the alternating series test and its error, the ratio test, and the root test. It's going to be tons of fun here. So let's talk about those comparison tests. First, we have the limit comparison test and the direct comparison test. And we want to know, when do we use them? They're used primarily when they look a lot like a series we know to converge or diverge, usually a known p-series or a known geometric series. Make sure when you use it that you state what known series you're comparing it to and why you know that series is convergent or divergent. So I like a statement something like, compare to 1 over 3 to the n, a known convergent geometric series with the absolute value of r equal to 1/3, which is less than 1. I like you to overstate all that criteria. And then you know the difference between the two tests and when to go to one versus the other. So let's discuss the direct comparison test first. That one we use primarily when we can get ours, the one we're working with, to always be above a known divergent or below a known convergent series. Then we can draw.
Remember that ours
conclusion
doesn't have
that
to
ours
be greater than the
is
divergent or less than the
Now
convergent
keep in mind
for
that
all
if we
values
are
of n,
under
but
a
just for
divergent
some
or
k
over a
along the
convergent,
way,
the
we
DCT
eventually
is
have to be
inconclusive. For the
riding
limit comparison
above on
test,
out to
we
infinity to
actually
conclude
run a limit,
divergent,
which
above
that's
a
why it's called the
divergent,
limit
or
comparison test,
below
as
from
n
that
approaches
value
infinity of the
on
ratio
out to
of two
infinity a
consecutive
known
terms,
convergent.
either
So
a
it's
to the n
not
plus 1
for
over n or a to the n
every
over a
n
to the n
from
plus
1 on
1.
up to
If
infinity or
that
2 on up
limit
to
of the
infinity.
ratio
It's just
is
at some
finite and
point
positive,
it must
we get
eventually
to draw a
ride over the
conclusion of
divergent
convergence or
or under it.
divergence. Let's get actual concrete examples of these. So when I look at 1 over 4 to the n plus 1, really I'm seeing 1/4 to the n, a known convergent geometric series. If I can get this one to be less than or equal to 1 over 4 to the n, I can conclude that this one converges as well by the DCT because it's under a known convergent. So we'd set up an inequality, 1 over 4 to the n plus 1 less than or equal to 1 over 4 to the n. And we know that 4 to the n is less than or equal to 4 to the n plus 1 for all n greater than or equal to 0. So we can conclude that this will converge also as being directly compared to a known convergent geometric series. Now for this one, although I could probably do the direct comparison test, it's not as clear that it's going to ride over or under a known convergent or divergent series. So what we do is the limit comparison test. If I had 3 to the n squared over n squared. Remember, n is the new x. And I'm taking the limit as n approaches infinity. I get 3, which is finite and positive. So if I do the limit comparison test with this series 1 over n, the divergent harmonic, then when I do the ratio
I'll actually be multiplying by a reciprocal. So I'll be multiplying by n over 1, and I'll get 3n squared minus 2n on the top. When I run that limit, it equals 3, which is finite and positive. So I can conclude that this series diverges as well, using the limit comparison test to the known divergent harmonic series. And then we stopped and practiced for a little bit. And in popped the alternating series test next, along with its error and the discussion of absolute versus conditional convergence. Ratio and root tests are still on their way. Tons of fun. So let's talk about the alternating series test. Make sure that you can state with correct notation what you are concluding and why. What do I mean by that? Well, first of all, we need to spot when to use the alternating series test. It's when we have embedded in our rule of sequence a viable alternator, like -1 to the n, or -1 to the n plus 1, or one of the sneaky alternators like cosine n pi. When we spot that, we usually try to run an alternating series test. We take the limit as n approaches infinity of the absolute value of the rule of sequence, meaning in the absence of the alternator. And if that limit equals 0, we get to conclude that the series converges by the alternating series test. So it's basically our second one-way test. Our other one was our nth term test for divergence. Alternating series is a one-way test for convergence. Normally, when we get that limit being 0, we can't conclude convergence or divergence. But in the presence of an alternator, a viable alternator, if the limit in the absence of the alternator goes to 0, that alternator will cause it to go to 0 fast enough to converge. Now, the discussion between absolute versus conditional convergence. If the series needs the alternator to converge, and we use the example of the divergent harmonic in the presence of an alternator. And we remember we ran that through our calculators, and we had n getting closer and closer to infinity, but not even very close. And we saw that in the presence of an alternator, there was convergence. So that would be called a conditionally convergent alternating series because it needs the alternator. In the absence of it, it is the divergent harmonic. Where if we were to do -1 to the n plus 1 over 1 over n squared, yes, that converges by the alternating series test because the limit goes to 0, but it doesn't need the alternator. So that would be called absolutely convergent. Then also make sure you know how to find that error or find an interval of convergence, or basically a window in which you know the sum must reside. And remember, that was all about the absolute value of the first unused term. Moving on, take a look at this one. And let's discuss in your head why this would be an alternating series. We have our sneaky alternator in the numerator. The limit in the absence of the alternator, or of the absolute value of a sub n, is equal to 0. So we would conclude that this converges by the alternating series test. But in the absence of the alternator, we have the divergent harmonic. So we would say that this converges conditionally. Then we moved on to the ratio test. Remember, the ratio and root tests are pretty similar. The root test is not tested on the AP test, so no one to try them. The root test is pretty clear because you see that rule of sequence to the nth power, so that one's pretty obvious. The ratio test triggers are those really fast-growing functions, Factorial is a big trigger for this. Factorial, battling it out with a exponential function, like maybe a 3 times 4 to the n on the top and a n minus 2 factorial on the bottom. When we have those really fast growing functions kind of battling each other out in the numerator and denominator, that's when we go to the ratio test. So know when to try them. Make sure you know how to simplify that ratio correctly with your factorials, writing them recursively, etc. And make sure you realize and state that you are taking a limit, and also make sure you include those absolute value bars. All right, so those ones had pretty clear triggers for them. So take a look. This has a trigger for the ratio test. I have a very powerful numerator, but I've got that king of growth, well, the queen of growth, because our n to the nth is the king, but we have very fast growing functions in both the numerator and the denominator. So this is perfectly set up for our ratio test. And in this one, we don't really have that super powerful function in the denominator. We do. Actually, we do, because that's to the nth power. Sorry, I misread that. It's kind of blurry. But this is set up perfectly for our root test, because I have n squared to the nth and 1 plus 2n squared to the nth. So I could make it the quantity n over 1 plus 2n squared quantitatively to the nth power. And then I could use my root test. All right, so that concluded all of our tests for series convergence and divergence. So now it's just time for you guys to practice, and you might even want to go through this and make a little study guide as well.